Hi gang. Today we want to start chapter 3. So chapter 3 in our textbook is titled Numerical Summaries of Center and Variation. Right. So here are the next slide. Here we're given some chapter 3 topics that we'll talk about. So we're going to talk about summaries for center and spread in symmetric distributions. So we'll talk about mean and standard deviation. And then also in skewed distributions, so median and IQR, which we'll learn as inner quartile range. Also, we'll look at some other summaries for variation, so variance, range, the empirical role in z-scores, box plots, 5-number summary, and outliers, and then also comparing distributions. So in 3.1, we have summaries for symmetric distributions, right? That's the title of this section. So in this section, we want to be able to look at some measures for center. So this is the balance point or the mean, and then also measure of horizontal spread, so variability, standard deviation. Right. So the next slide, we're going to look at some appropriate measures. So you want to recall that when we've been dealing with numerical data, we need to describe the distribution using these three characteristics, right? So this should be, you should see a theme here of these three things keep coming up and up and up, right? So when we do descriptive statistics, these are the three things that we want to be aware of, right, with numerical data. We want to look at the shape, right? So remember what that means. We're looking at, is my distribution symmetric? Is it skewed to the left, skewed to the right? Is it uniform distribution? Is it bimodal, unimodal, so forth. Next, we want to look at center, right? So remember, when we look at center, we want to try to find the typical value. And then also the spread. So this is the horizontal variability. Right. So in chapter 3, we're going to focus specifically on center and then spread of a distribution, right? So we're going to go more in depth in these two characteristics. So the mean, one way to think about that is as a balancing point of the distribution, right? So, for example, if I take a look at mean salaries of RNs, right? Then what this means is I'm going to take up all the money of the RNs, right? So we're going to have a pot of money. So in this pot, we're going to put all the RN's money, right, all their salaries into one pot. And then we would evenly distribute it, right? So then all RN's make the same amount. Right? So if we were to do this, that same amount that every RN would be getting is referred to as the mean, right? So that's why we call it the balancing point of the distribution. So what's the point that would balance everything where everyone gets the same, right? So this slide, we have a symmetric distribution, right? So the diagram there is a dot plot, and it's showing distribution of ACT scores for some sample of statistics students, right? So one note here is that for symmetric distributions, the mean is good at a representation of a typical value of the data set, right? So you can see this triangle here. This is showing where the mean is, right? So that is a good representation of the typical value, right? So right? Because we have a lot of values around it, right? So we can call that typical, right? Where like this value over here would be atypical, right? It's kind of by itself. There's not a lot of data points near that, right? It's like an extreme value. Right? So just one thing just to catch here, right? So remember when we talk about center, we're not saying cut our data like max and min and find the value exactly in the center, right? I mean, our center could be there, but that's not specifically what we're meaning, right? So the center is what's the typical value, right? So we're like, where's most of our values at, right? That's the center. So here we're looking at the mean, but with skewed distributions. So we can see here with this histogram, we have an example of a right skew graph, right? So we have this overall shape distribution, right? So here, remember this is called the tail, right, on this end, and this would be right skewed, right? Or some people refer to this as positive skewed. Um, I believe that's also described in the text, right? So it says the distribution shows the salaries of professional baseball players in 2010. So the question is, do you think the mean is a good representation of the typical baseball salary for that year, right? So here, this represents the mean. Do we think that this is a typical baseball salary, right? So the answer is no, right? So it turns out that the mean represents a typical value in a set when the data is roughly symmetric. So if we have a skewed distribution like we had above, then the mean is not a good estimate of a typical value, right? So in this section, we're going to explore some other typical values and what might be better for something that's skewed. Right. So to compute the mean, right, we can think of this as two ways. So if we have small data sets, then we simply just add all the data values together and then divide by how many numbers we have, right? So one way to represent this, right, so we use x bar to mean my mean, right? So x bar would be equal to all the x's added together, right, divided by n, right, the number of data points that I have, right? So that's what this notation means, right? This is Greek letter sigma, which simply means to add, right, to sum. So what this is saying is sum all the x's and then divide by n, right? So divide by how many we have. So we can do this very easily for small data sets, right, by hand. But if we have large data sets, which is typically what you would do, if you're doing this on the job or for some project, you might have 1,000 pieces of data that you want to use, right? That's very cumbersome to do by hand. So we want to use some appropriate technology in order to be able to do that, right? And that's one thing I'm trying to give you some skills on. So here is example. So suppose that we have a sample of prices for 1 gallon of regular gas at 10 different gas stations in a particular neighborhood in Austin, Texas. And this is taken all on one fall day in 2013, right? So all of these gas prices are from one day. We want to be able to find and also interpret the mean, right? So in order to find the mean, right, again, remember we're going to add up all the x's and divide by how many we have, right? So we would want to take, 3.19 plus 3.09, so forth, all the way until we get to 2.97, right? Find what that sum is, and then we have what, 1, 2, 3, 4, 5. We have 10 gas stations, right? So n equals 10. So then we would divide by 10, right? So we're putting all the costs all together in one pot, and then dividing by 10 gas stations, right? So that way everybody charges the same amount of gas, right? Essentially is how you can think about it, right? It's the balancing point. So if we look at the next slide, so what we've done here is just took that gas price data and plotted it in a dot plot, right? So the question here says, what do you think a good estimate would be for a typical gas price for that neighborhood, right? Right, so one thing we can do is find the mean, right? So I started writing this out by hand, but this is all typed out for you, right? So we take 3.19 plus 3.09, right? Add up all the data values together, and then divide by 10. And then in doing so, we get approximately 3.02, right? If we round to the nearest hundredth, 2 decimal places, right? So a way to interpret the mean, right, we can say the following. We can say the typical price of 1 gallon of gas at these gas stations in Austin, Texas was $3.02 on this particular day in 2013, right? So that's what we can conclude about that. Right, so you want to be careful with being able to interpret the mean also, right? So here, going back to our dot plot, right, our mean would be about here, right? So if you want to draw that with, or show that with the triangle, that's fine, right? So our mean would show up about here, which seems to be an okay measurement about the center, right? Typical value, right? We have data points on the left, data points on the right. It seems like it would be a good balancing act for these data points. Right. So another way that you can find excuse me, find the mean of that is we could plug this into our calculator, right? So there are directions here on this slide. So let me open up my TI graphing calculator. So I'm going to input the data points from the gas station. So let me go split screen here. Alright, so I'll go back up where we have the data points listed. So to do this, you want to go to the stat button right here above program, click this, and then we want to hit enter. We want to go to the edit, right, option 1. So I already have things in my list, so you can just delete each one of those, right? You want to make L1 be empty, right, if that's where you want to input data. If you have a very large amount of things in here, you can also go hit second and then hit the plus sign for memory. And then you can notice here option 4 is to clear all lists. So we could hit option 4, hit enter, and it's telling us it's done. It cleared all of our lists, right? So it would clear all those out for us, right? So if I go back to stat and I want to go to edit again, now I can input my data all into L1, right? List 1. So we would hit 3.19 and then hit enter, and then 3.09, enter. So keep doing this until you enter all the data points in. So 2.93, 2.95, 3.09, 2.99, 2.99, 2.95, and 2.97. Right, so all of those should be in there. So now what I can do is I can go back to stat, hit the stat button, and then click 1 over, so you get the calc at the top. And then you want to go to 1 variable stats, right? So if I hit enter here, so I'm telling that I want L1, so we can tell it to calculate, right, from L1. So now notice I have some data values listed, right? So we can work on interpreting that. So let's see, what was I looking for? Oh, here where I calculated the mean, right? So X bar, of course, is the mean. So 3.0204, right? So that tells you this. Some of the X's, this tells you if you add up all the X values what you get. So in other words, this is the numerator in the mean, right? Sum of X squared, right? That means you took every value, squared it, and then you added all those up. These next two we're going to talk about in a few slides, right? So we'll come back to this. And then here, n equals 10, right? Remember that tells us how many data values we have. And then we can also go down and we get more information like min, quartile 1, the median, quartile 3, the max, so forth, right? So those are other things that we're going to explore in this chapter also. That's referring to the 5-number summary that we saw early on, second slide, right? Talking about what we'd cover this chapter, right? So that's how you could do that on the graphing calculator, right? So the graphing calculator is very nice, and you should be able to do something like that on an exam, right? You can use that to double check yourself. I might ask you to write it out by hand, depending on how many values we have. But this is a great tool to use, right? All right. So then next we have measuring the spread, right? So you want to recall that the variability in distribution can be measured by the horizontal spread, right? So let's consider that, the horizontal spread. So the question is, why care? Well, we need to know if most of the data is near the center or far from it, right? Because that's a big indicator for how the spread is going on, right? How our data looks. So if we assign a number to the horizontal spread, it's not so straightforward, right? So a way that we can measure this spread, we'll be exploring the following example, right? So we're going to look at standard deviation. So here we're told that the following histograms record the daily high temperatures in degrees Fahrenheit over one recent year at two locations. So we have Provo, Utah, and San Francisco, California, right? So in Utah, the elevation is 4,500 feet, where San Francisco is at sea level, right? So it's a little different. So one thing, so we want to look at these two histograms, right? And on the next slide, we have these listed here still, right? The same histograms. So some things I wanted to note is that both of these distributions have roughly the same shape, right? They're both symmetric, and they both have a center that's in about the same spot, right? So in Provo, I estimated that to be about 67 degrees, right? The center, where in the San Francisco example, I would probably put that at about 65 degrees, right? But if you notice, the spread in both of these histograms are very different, right? So in Provo, we have more spread out, right? Which means my data values are farther from the center, right? So much more spread out compared to the San Francisco example, right? And notice that the x-axis is the same on both histograms, right? So we can really compare those, right? So that's one thing you want to make sure that you notice when you look at histograms, because some things could look different just because they have a different axis, right? So then, again, as I was saying, a way we can measure spread is standard deviation. So standard deviation is a number that measures how far the typical observation is from the mean, right, the center. So we're looking at the average distance from the mean for all the data values, right? So we're told that for most distributions, a majority of the data is within one standard deviation of the mean, right? So if we find the standard deviation of the mean, that's going to be in the same units as our data points. And when we talk about one standard deviation, we're going to talk about a set number of units away, right? So if we're talking about test scores, our standard deviation is going to be a set number of scores away from the mean, right? So you can think of, for example, like a yard is 3 feet, right? So one standard deviation is going to be so many test scores or whatever we're talking about, right? But it will be in the same unit as our data. The one thing to note also is that we want to think of the standard deviation as the typical distance of the observations from their mean, right? So I have that written here, and I said that just a moment ago, just using some different words, right? So then here's an example of standard deviation. So it says the graph below shows the distribution of the amount of particulate matter or smog in the air in 333 cities in the United States in 2008. So this was reported by the EPA. So we're told that the mean of the particulate matter is 10.7 micrograms per cubic meter, and the standard deviation is 2.6 micrograms per cubic meter. Right? So let me make note of that. Right? So we want to write that down. So it might be helpful. So I'll write off to the side what I'm going to write down on a piece of paper on my desk, right? So what we want to write down is the mean is 10.7 and the standard deviation. So the symbol we use for standard deviation of a population, we use S, right? So we would say S equals 2.6, right? And see why I'm thinking about this also. So we've talked about mean and standard deviation so far. So mean and standard deviation. Right. So we'll do here population and sample. Right? So one thing you want to remember when we talked about population and sample before, right, is if we're trying to do a study, we can never possibly know or be able to get results from everything in the population we're studying, right? So like in this example, we're studying smog levels in cities in the United States. It's not possible, it's not practical for me to get a sample from every single city in the US, right? But what we can do is we can take a sample, which is a portion of the population, to estimate the mean, or not the mean, but the estimate for the population, right? So we take a sample and try to estimate what the population would look like, right? So when you think about this, I mean, certainly we're going to learn about some techniques on sampling and what's the best way to be sure that your sample is going to be a good indicator of what your population would look like. But we understand, we know that we're never going to be exact, right? We can't use a sample and get exactly what the population mean would be, for example. So the population and the sample mean we know are going to be different, right? So we use different symbols to denote that, right? So for the sample mean, we use X bar, right, to denote sample mean. And for the population mean, we use mu, right? And then for standard deviation for the population, we use sigma. And then for the sample standard deviation, we use S, right? So if you notice, the population characters are Greek letters, where the sample ones are not, right? So that might help you remember the difference, right? And as we explore other variables, I'll remind you of what the symbols will be, right? All right. So back to the example. This is what we'd want to write down, right? I just wanted to explain so you knew what where the S was coming from. All right, let me grab my pen. All right, so we have X bar equals 10.7 and S equals 2.6. Right, so we're going to need that in a moment. So then on this next slide, it says find the level of particular matter, one standard deviation above the mean and one standard deviation below the mean, right? So in other words, what this is asking me to do is take the mean and add a standard deviation to it, and then also take the mean and subtract one standard deviation from it, and that will give me the question number 1, right? And I did write SD. So there are other books, like the quantitative reasoning book has some statistics in it that I also coordinate and teach, and that book uses SD for standard deviation. So that's fine, or you can use S, right, as I said before, right? So either one. And then number 2 says, keeping in mind that the EPA says that levels over 15 micrograms per cubic meter are unsafe, what can we conclude about the quantity of most of the cities in the sample, right? So those are the two questions that we have. Right, so number 1, right? So this is the level of the particulate matter, one standard deviation above and below the mean is the following, right? And notice this is the standard, notice that this is the standard deviation and this is the mean, right? So both of these have the same units, which means our answer in the end will have the same units, right? So standard deviation has the same units as your data values, right? And remember what we did here is we took the mean x bar, added the standard deviation to it, and we got 13.3, right, for the first one, right? So you take the mean 10.7, add the standard deviation 2.6, and you get 13.3, right? And then for this line, we took x bar minus s to get 8.1, right? So we took 10.7 minus 2.6 and got 8.1 micrograms per cubic meter, right? So remember the second question, right, is remember anything over 15 micrograms per cubic meter are unsafe. So we're trying to think about what can we say about our data. If you remember previously above, so what we know is that most of our data values, so our data will fall within one standard deviation, right? So if we draw like a number line, right, here is x bar, which was 10.7, and then here is so this would be 13.3, and let this over here be 8.1. Then what we're referring to is that this distance in between is one standard deviation away, right? Which our standard deviation is 2.6. So when we say one standard deviation within the mean, we're talking to the left and to the right, right? So we need to do those, have that distance. So in between this interval, 8.1 and 13.3, most of our data will fall in here, right? We're going to talk about this more specifically in the coming sections, right? We can talk about the actual percentage of data we could expect within 1, 2, and 3 standard deviations, right? So forth. So then the next slide here gives us the formula for the standard deviation, right? And I'm going to walk through some examples with that, right? So this x minus x bar, right? We're taking every x, subtracting it from the mean. This is going to tell us the deviation or the distance of our particular observation from the mean, right? So that's what that does. And then number 2, we're going to square it to make it positive, right? Because we need our distance to be positive. And then 3, we're going to add up all these squared deviations, right? And then step 5, we're going to divide by 1 less than the sample size, and it says see text, right? So think of this as averaging the squared deviations, right? So what you would learn in the text is that we need to divide by n minus 1 to make this a better predictor, right? So you want to remember that here we're doing this based off the sample to estimate the population. Well, if we just divide it by n here, it's not going to be a very good predictor. So it turns out that if we divide by n minus 1, it's a better predictor of what the population standard deviation would be, right? And then lastly, step 5 is we need to take the square root to return it to our original units, right? Because since we squared it, if your units were in inches, now suddenly they're in inches squared. But then when we take the square root of inches squared, then we get just inches back, so we're good to go, right? So we want to return it back to our original units, right? So then here's an example of finding standard deviation, right? So this is looking back at our gas example, right? So we have 3.19, so forth. So the same gas prices as before, right? So then here in this table, this shows you what you would do, right? So I like to make a table with this. So we make a table for x, right? In this column, list all your data values, and then the next column, you're going to take x minus the mean, right? So you're always taking whatever's here on the left minus the mean, right? So minus 3.2. And notice if you get negative values like here, that's because these values are less than the mean, right? So if you get a positive distance here, that means it's to the right of the mean, that value. And if it's negative, it means it's to the left, right? And then in this column, all we're doing is taking whatever values here, and we're squaring it, right? We're putting in here and squaring it, and we're getting these values. So then, if you remember right, the equation, right, from above. So we have the square root of, so we want to take the sum of the x minus x bars, right, the deviations, and square it, and then divide it by n minus 1, right? So sigma x minus x bar would simply be just adding all these up, right? So if I add all these up, so sum all of these, that's what this notation is, right? So this is adding all these up, right? So we would take 0.0289 plus 0.0049, so forth, add all those up, we would get this, right? And something to keep in mind is I don't believe any of these were rounded, but our mean was rounded. So we're using a rounded answer to get an answer, so we will have a little rounding error. So our value calculated from this might be different than if we used R or Excel or even our graphing calculator to get a more exact value, right? But they should be close, right? So that's what this is saying here, is note that this is going to be slightly off because of rounding the mean, right? Using a rounded answer to get another answer that has a rounding error, right? So doing it this way, you should get this approximation, right? 0.0855. So if we go back to the graphing calculator, right, that we had up, all right. So here where we have SX, this is my sample standard deviation, right? So this theta, right, if you remember, this would be an estimate of my population standard deviation, right? So S of x we have 0.085, and then we got 4 from the calculator, right? And here we round that to 5, right? So there is a little off, right, as you can see, right? So using a calculator or technology is the best bet, but being able to do it by hand is important, because then you know how the formula works. You have a better understanding for what standard deviation is. So when you see the number, you can more easily interpret it. So like for the midterm exam, you're going to want to be able to do both, right? You're going to want to be able to calculate this by hand, same with the mean by hand, and then also be able to plug in your TI graphing calculator and find those values, right? So on the exam, you won't be using R or Excel, but we do have Excel and R assignments to practice those skills outside of class, right? So inside of class, I'm expecting you to use the graphing calculator, right? Right. So what we know, right, just to interpret this, so we know that the mean is 3.02, right? And the standard deviation is about 9 cents, right? So if we round that to the nearest cent, we get about 9 cents. So how to interpret this is we can say that at most of the gas stations, the price of a gallon of gas is within 9 cents of 3.02, right? So we could expect most of our gas prices to be in between 3.02 minus 9 cents and in between 3.02 plus 9 cents, right? So 3.02 minus 9 cents would be what? 2.93, right? And then 3.02 plus 9 cents would be $3.11, right? So most of my gas prices are going to be in between these values, right? So then here's just another slide that I already showed you how to do, is how to do this on the graphing calculator, right? So then this last slide that we have is just what variance is. So variance is simply taking the standard deviation and squaring it, right? So notice the symbol that we denote that by is s squared, right? So for variance, and then also do for standard deviation, right? So for a sample, right, I denote standard deviation as s. So then the variance of a sample is s squared, right? But the standard deviation for the population is theta, right? Or sigma, theta, sorry, that's theta. So then for the variance for the population, of course, would be theta squared, right? All right, so it's the same equation we just squared, right? So what happens when we square it? We are removing the square root then, right? But one thing that you want to note is that by squaring it, we are not going to be in the same units as our original data, right? Remember, that was the whole reason of having the square root symbol, was to put our units back into the units that we are working in. So variance typically is less preferred than the standard deviation, but that's an option also, right? All right. So now what I would like to do is go over problem 24 on page 123, right? So this is an example from this text. So what we're told is a survey on StatCrunch asked people to report their level of happiness from 1 being least happy to 100 being most happy. This table shows a sample of 20 female and 20 male responses, right? So A says that we want to make 2 separate stem plots or dot plots or histograms. And we don't want to forget to show empty cells if you're making a stem plot, right? So it says, are the distributions skewed? If so, which way? Compare the means, compare the standard deviations, right? All right, so I put on Canvas an Excel file for you that you can use. So I went ahead and entered in all this data. So I titled this question 24, right? So I saved this as a .csv file. So I want to show you how we can use R to help us with this, right? So I'm going to open up R. Right. So remember, the first thing that we want to do, unless you are typing in your data by hand using the C command, right, which I've shown you before in a previous video. Then the first thing you want to do is set up your working directory, right? So we want to do, first I always do get wd with parentheses, and this tells me where my working directory currently is, right? So remember, your working directory is you're telling Excel, hey, this is where I'm working, right? So then we can go to set wd, and I'm just going to copy what's up here. And I like to work in my desktop, right? Whoops. So notice here I accidentally hit enter. I didn't mean to. Went down to the next line, has this plus symbol, and it's not letting me go back up in here. What I can do is I can just hit this stop command up here. It says stop current computation, and it will just bring me down to a new line, right? So if I hit the up arrow on my keyboard, I can cycle through what was previously done, right? So now I can just hit the backspace, and I want to change this to desktop, right? Close my quotes, and then close my parenthesis and hit enter, right? So remember, nothing here is good, right? My working directory worked and went through. So then now what I want to do is grab my data. So I'm going to call my dataset data, and then we need to do the read.csv format. Remember, your Excel file has to be saved in a comma separated value format, the CSV format. So if you open up Excel, right, when you go to File and you go to Save As, and you pick where you want to save it, this where it says Save As Type, right, you want to pick CSV comma delimited from your drop-down menu, right, CSV format. Right, so I won't save it because I already have it saved. So my file name was question24.csv. Right. Oops, that's happening again. I don't know why. Oh, it's because I forgot to close the quotation mark. Right. So close the quotations, close the parentheses. Now we're good to go, right? So again, nothing is good here, right? I'm not getting an error message meaning something's not working. Now I can go to attach my data. So this is now I told Excel what data is, right? What file I'm calling data. Now I'm telling Excel, hey, when I do commands, I want you to use data, right? And then I also like to do names of data. And what this does is tell me what variables I have, right? So R reads, you know, at the titles at the top, right? So let me open up this Excel document again for you. Right, so remember how Excel reads this, or how R reads this is, you know, this is one variable, this is another variable, right? Right, so what Excel was telling me when I do the names is what's up here, right? So now when I refer to female, or R knows I want all these values, right? So then if I go back to R, right? Right, so I have that ready. So if we go back to the question, right, what we were asked to do is we could do stem plots, dot plots, or histograms. So I'm going to do histograms, right? So if I do histogram of female, right, then I have that here, right? So this is what the histogram of the female looks like, right? So we want to know if anything is skewed, and this is definitely skewed, right? So let me copy this, right? So I copied as a meta file. I'm going to go back into my notes here, and I'm going to paste this here, right? So I can draw on it. So if you notice, the overall shape looks like this, right? So if you remember, right, we refer to this as a left skew, right? So this is left skewed, right? So it doesn't look symmetrical, it definitely looks skewed, right? So then I can go back into R, and I'll just close out of this, right? And then I'll type in a histogram for male, right? So I'm telling R to make a histogram for the male variable, and again, this also looks left skewed, right? So you can kind of see the overall distribution, right? So we do have scores of 0 in between this range, but I would still call that left skewed, right? So both the female and the male histograms are left skewed, right? So that's what we would say for part A, right? So then part B says compare the means. So if I come back into R, I can do mean of female and get that. I can do the mean of male and get that, right? So the female mean was 70.2 and the male mean was 64.25, right? So what we could say is that the typical happiness level is higher for the females, right? So the typical happiness level is higher for the females, right? That's what we could conclude from that, right? So that's part B. So in part C wants us to look at the standard deviations and also interpret that. So to get the standard deviation, I do the SD command, right? So we do SD of male, SD of female. Whoops, shouldn't have that slash, right? So there, now I have that. So I have the standard deviation of the female and of the male, right? So for the male, we have 35.86 roughly, and for the female, 28.55, right, roughly. So what that tells us is that the variation in happiness rating is greater for the males, right? So the greater the males show more variation in their data, right? Which makes sense looking at the histograms also, right? All right, so that's all I have for this section. So if you guys have any questions, you know, feel free to post in the discussion board or send me an email.